Let's just look at a possible direction field, okay?
One thing that we try to do is the stats to understand variation. All right, 100%.
Let's also ask ourselves about the range of the solution. So, direction field.
The data you use. Right, and therefore the probability, and in reality the probability is the continuous number purple. It's actually zero. Right, let me give you an example. Let's say I was going to stand here and say I'm trying to figure the average age of students in this class. I'm going to do that by grabbing a bunch of samples, right? Samples. I'm going to say the samples turned out to be this, therefore I believe the real exact number is that. Is how we're taking this inferring, drawing a conclusion. What's the probability that I get the average age? Absolutely. You'd be like, oh, what's that mean? Because I think the average age is 19.
Okay, here's a segment of a direction field. Don't know where the x-axis or the y-axis is, but they're somewhere. Okay? And our point t naught, y naught, well, if our point t naught, y naught is here, it sort of appears that our solution's going to do something like this. Oops. My hand was covering what I should have been looking at. Might well look like this. And if these slopes approach infinity, so the slope is undefined, to where it approaches plus or minus infinity, clearly you're not going to get past that point, right? Okay? So, no matter where you are between these two vertical lines, you're going to be confined between those vertical lines in your solution. Okay? Now, if you're on the other side of the vertical lines, let's draw a green solution over here. Okay, so let's say you're on this side. So let's say that here's your T naught, Y naught. Okay? Well, what's going to happen? Well, your solution's going to be like this, and over here it's going to be like this, and you're going to have this, right? So solution is not going to exist. It's not going to be defined on this side of this vertical line. Okay?
So those are two separate solutions?
Well, yeah, depending on where you start, you could have two different solutions. Just like the problem we started with. You ended up with a vertical asymptote, right? Now, if you'd have started to the right of that vertical asymptote, you would have had a solution, but it would have been a completely different curve than the one you have, because the curve you have becomes undefined at the asymptote. It ends there. Okay, it does not go past the asymptote. Well, the curve on the other side probably approaches the same asymptote, either up or down, okay? But it won't be defined on this side. Well, that's the essence of the existence theorem. So, to make a statement, the solution the domain of the solution is confined between vertical asymptotes of this f of t, y of t function. Okay? And I'll say one solution is confined between vertical asymptotes. Of the f of ty function. Okay? And that occurs if t naught's between the vertical asymptotes.
What is the function f of ty?
In the case of the function we just saw, it was x squared y. We just did it for f of ty equals x squared y.
So that's your differential equation?
Yeah. This is a differential equation. It relates the derivative of y to the independent variable and the function y that's a function of the independent variable. Okay? Okay, so this occurs if t naught is between the asymptotes. Okay? And let's make the condition that as we move to the right, the slopes approach zero. So this thing just kind of smooths out, right? So you have a maybe a vertical asymptote, but maybe they don't approach zero slowly enough to actually give you an asymptote. Like if this was a square root function, it doesn't approach a vertical asymptote. If it's an exponential approach, you know, some constant minus an exponential function, then it does approach a vertical asymptote, or a horizontal asymptote. Did I say vertical? Anyhow, you get the idea. And of course there, it's really important to understand exponential functions and square root functions and the nature of their, the nature of their graphs. And the nature, just the behavior of those functions, just so you can see examples of different behaviors. Okay, so, then there would be another solution over here. And of course there could be another vertical asymptote over here. This thing could go negative here, and you'd be confined between these vertical asymptotes if your t naught was in here, right? Okay. Well, there's a more formal statement of it. There are conditions, there's like absolute continuity and absolute bounds and stuff like that on this function, okay? Which gets us into what's now usually taught in an analysis course and isn't taught in a calculus course, okay? So I'll mention it, I'll wave my hands over it, but there are some pretty sophisticated conditions on this that I think you're in shape to understand, but I'm not going to take the time to talk about them right now. So basically the existence theorem at least says this. It says a little more, but this is really pretty much what you have. Okay? Now the range of the solutions, well, if there's a line across which the slope is zero, that could bound your range, but doesn't necessarily. We just saw an example. On the y-axis, the slope was 0, but the function went right on through that, right? It's also possible a function could just approach a horizontal line where the derivative is 0 as an asymptote. Okay?
We did both.
Huh?
The one we did both.
Well, yeah, we had an asymptote at the x-axis, exactly. Good observation. Okay? So, I'll just say, existence theorem says this. As long as f and its derivatives behave nicely. Okay? And this behave nicely gets into some more advanced concepts that you still are going to see when you look at the existence theorem. Okay, and the whole history of the development of the existence theorem is pretty neat. Involves some, you got this thing called the Lifshitz condition. Okay?
He sounds German.
Huh?
I'll bet he was German.
Yeah, yeah. We might talk about that. So it's kind of interesting. It gives you a little preview of why higher mathematics.
Goody goody.
Huh?
Goody goody.
Is useful and important in many fields. Like if you're an engineer, usually doesn't make any difference. But there are places where it does, where you really have to understand the more sophisticated behaviors and dysfunctions. Otherwise, you end up in deep trouble. Incidentally, I sent Mr. Tidwell a link to an article that I thought was fascinating. And since you're in a materials class, it's totally relevant. Talking about building an 800-foot skyscraper out of wood. Pretty neat. Pretty neat looking. A lot of triangles.
How long would it stand?
They think it'd be just as stable as a concrete and steel structure.
Really?
Right now it's theoretical. You know, they've done computer simulations. And, you know, the problem with wood, one of the advantages is it sways in the wind more easily than steel, which is great until you get too much wind where it breaks. Okay? And you control that with enough triangles. And the details of it, you know, just draw yourself a free body diagram of every joint in that skyscraper and work it out. And naturally, of course, you're going to use a computer to do that, but you got to understand free body diagrams before you can even start, right? And you got to understand strength of materials. Okay, things like tensile strengths and bendability. You have official words for that. Okay, and limits on how much the second derivative of the curve can, how high the second derivative of the curve can be. And you'll appreciate that when we talk about waves in physics, as we're already doing, okay? Because the force that restores a point on a wave to toward the equilibrium position is proportional to the second derivative of the curve. Okay? I wanted to say second derivative of the curve in space, but I decided I didn't need it in space. Okay? At least not at this point. We've got to be real specific later. Which leads you to the differential equation. Since the force is proportional to the second derivative of the curve in space, and the force is proportional to the second derivative of the position, the transverse position, you have the second derivative with respect to time being proportional to the second derivative with respect to position. And that's the wave equation. And it's already in your homework. Okay? You're going to love it. And the diffusion equation just relates to the first derivative of the diffusion rate, let's say, to the second derivative of the concentration function. Kind of interesting. Okay. And of course, that's all differential equations, which is why I mentioned it. And since we're talking about waves in physics, you might have some clue about what that means. And then you go ahead and do complex probability functions in quantum mechanics that behave according to similar equations with complex solutions, which you'll appreciate. Probably already do, because I think one of your homework problems had a complex solution. Yeah, well, if it didn't, you'll see one soon. It's just, you do your characteristic equation, you assume that y equals a multiple of e to the RT, plug it in, and you get a quadratic equation. Well, that quadratic equation can have real, imaginary, or complex solutions, depending on the numbers. Okay? And some of those numbers give you sine waves. Some of those numbers give you exponentials. They all give you exponentials, but some of the exponentials are trigonometric. And that's really pretty easy to understand when we do it in detail. Right now, I just want you to be able to do the characteristic equation and know your basic premise that when you have a higher order differential equation with constant coefficients, you always assume a solution that's an exponential, an e to the RT type thing. Then you get a polynomial that you got to solve, set it equal to 0 and solve. And that tells you what your possible solutions are. They form a solution set, which is linearly independent if the Wronskian, which is a simple determinant, is not 0. And there you have second order and higher order equations. So it's really conceptually very simple. The details get a little challenging because your trigonometry has to be good. Your function trigonometry. Okay. Anyhow, you have that to look forward to, but it's not bad. Okay. Yeah, we have about 10 more minutes.